Zoom the recording. There we go. Okay. Okay, so let's jump into chapter 9 here. Okay, hypothesis testing. Okay, so for hypothesis testing, we want to understand the logic of a hypothesis test. We're going to set up what is a hypothesis test today, and we're going to go through, you know, what does it mean and what's the conclusions that we can draw. It's basically a comparison to what we think is true to what our sample says, and does our sample line up with what we thought was true or not. Okay. Number 2, interpret the meaning of a p-value of a hypothesis test. We're going to define what the p-value is and the hypothesis test, and interpret it in terms of a hypothesis test as opposed to a confidence interval. Okay, number 3, define what means to be statistically significant. Okay, and then 4, use the 5-step process for the 1 proportion z test. Okay, the idea of a hypothesis test, we wish to test whether or not a claim about a parameter, in this case, it's going to be P, the population proportion, okay, the parameter is true or not. Is it true or not? So this is the claim, okay, the claim, say that the claim, you know, so we have a claim, okay, that P is greater than 0.52. Okay, that's our claim, is that our population proportion, okay, is greater than or equal to 0.52. That's a claim. Okay, so population proportion. We could also have a claim based on averages, in which we'd have mu. Okay, so let me write out the claims here for A, B, C, and D. Okay, for part A, will at least 52% of the voters approve measure B? So the claim here is P is greater than or equal to 0.52, at least 52%. Okay, that's the claim. Okay. Part B, Jerry claims that his car averages 37 miles per hour. So that's an average, not a proportion. So that's mu, okay, is equal to 37. That's the claim there. That's the claim. And we're going to say, do our statistics line up with our claim? We're going to do proportions today and means on Thursday. Okay. Okay, part C, do people under the age of 25 have more accidents than people over the age of 25? Okay, so this is a comparison. We would say, do mu under 25, okay, or mu 1, are they the same, okay, or are they more, sorry, are they more than the people over 25? Okay, so we would set up 2 comparisons there, an average for the number of accidents that the people under 25 have compared to the number of accidents that people over 25 have. And part D, is the proportion of men who enjoy watching ballet higher than the proportion of women who enjoy watching ballet? Okay, so again, this is a proportion, so this would be P1. Okay, is that greater than, okay, P2? Okay, is P1 greater than P2? Okay, so different things that we're comparing. The problem, we don't know, and often can never know, the true value of the parameter. We don't know what these parameters are, P, mu, mu1, mu2. We often just have a sample. Okay, so thus we can never prove, we can't prove it actually true. what we can do is we can show the parameter is uh, it, uh, is either close or it's far away from our statistics. Okay, we can never show that a parameter is equally exactly equal to some value. We can't do that because we don't know the exact population proportion or the mu, but we can say whether or not the claim is close. Okay, we can say that we are 95% certain that the claim is either bogus or that it could be true. It could possibly be true. Okay, what can we do? We can use a statistic, one that is unbiased estimate of a parameter, as evidence. Okay, evidence, so a sample. Remember, a statistic is a sample. Okay, as evidence as whether or not the given claim is true. Okay, we're basically detectives. Okay, we're detectives. We're statistical detectives, and we're going to either say that it's true, okay, or not true. We would never say that it's true, that the claim is true. I don't want to say this, whether or not the given claim is true. We would say that the claim is false or plausible. Okay, plausible. Is it false or is it plausible? That's what's meant there by true. I got to change that word there. Okay, so we're detectives. We're saying, is it false? Is the person guilty? Or is the person not guilty? Now, not guilty doesn't mean innocent, right? I mean, they still could have committed the crime. There just wasn't enough evidence to convict them. That's the idea here. We're detectives and we want to know, is the claim false? Can we say statistically that that claim is false? Or is that claim plausible? Okay, is it false or plausible? Okay, in the US, putting a claim on trial. In the US, if a man is on trial, then our judicial system, we must assume the man is innocent. We gather evidence. Okay, we show that if he really was innocent, this evidence would be extremely unlikely. Thus, it is more likely to believe that he is guilty. Okay, okay, so it's the same thing. The logic of hypothesis test is we assume the claim to be true. Okay, assume the value of the parameter to be true. We gather data as evidence, and we show that the given assumed parameter value, the data in light of the data and statistics, would be extremely unlikely. Okay, so it's extremely unlikely. Thus, is believed that the presumed parameter value is not true. Okay, not true. So we can basically call BS on the claim. Okay, now we can never be 100% sure that the claim is false. Okay, but we can be pretty convincing. Okay, we can be pretty convinced. Okay, more formally, define the null hypothesis of what we wish to assume and the alternative. Okay, so what's the null and what's the alternative? Okay, look at the data and calculate the statistic. Number 4, find the probability of obtaining the statistic given our null hypothesis is true. Okay, assuming it's true, how far away is our statistic? Okay, that's our p-value. And number 4, if the probability of the result is small, we reject the null hypothesis due to sufficient evidence against it. Otherwise, we fail to reject, we fail to convict due to insufficient evidence. We have insufficient evidence here. Okay, example 1. Jessie takes a 20-question true-false quiz. She claims she guessed the entire quiz. Would you believe her claim or reject her claim if she got 11 out of 20 correct. Well, if she got 11 out of 20, that's pretty close to half, right? 50-50. And if it's a true false test, well, what's the chance of just randomly guessing and getting a question correct? Well, it's 1/2. It's 50%. And if she did that on every question, she could presumably get about half of them correct. So would you believe her claim if she got 11 out of 20 correct? Yeah, that's believable. Okay, but for 19 out of 20 correct by just guessing, that's pretty unbelievable. Okay, so I'm going to put a no there. Okay, and that's pretty unbelievable. That's to say that you know, she claimed that she got 50%. Okay, but our statistic, the actual results, is 0.95%. Okay, or 95%. So she claimed that she guessed, which means that she should have got 50%, but she walked away with a 95%. That's way far away from what she's claiming. Okay, and we could actually statistically see how far away this 0.95 is the sample statistic or the known statistic away from the claim. Okay, so I would say no, that's way far away. Whereas from 0.5, how far away is 11 out of 20? That's 55. That's 0.55. Okay, well, is that close? Yeah, that is close. Okay, if we were to look at a normal distribution here, and we were to say that the claim is that she got 50%, well, what's the probability, right, that she got 55? Oh, it's not too far. What's the probability that she got 95? Well, now we're probably somewhere way far away from 3 standard deviations away from the mean. Okay, so that's the idea. The idea here is for proportions, we're going to use a standard normal curve and say, hey, is it probable or is it not probable? Okay, deal or no deal? Okay, 5-step method. Okay, 5-step method to a hypothesis test. Define the parameter. Okay, define the parameter on the hypotheses. Okay, the null and the alternative. Okay, the null always is the one that has the equal sign. Okay, null is always equal. Okay. Okay, we're going to name the test. What are we testing? We're going to check the requirements. Okay, are the requirements met to use the proportions? Is it a prop Z or is it a T? Okay, is it a prop Z or is it a T test? Okay, with the prop Z test, okay, or is it a T test? Calculate the test statistic and the p-value, and then interpret, okay, in a conclusion sentence. So don't forget number 5 here. It's very important. Interpret. Are we going to accept the claim? Or are we going to reject it? Okay. Okay, the null hypothesis. The claim that we will assume to be true. Okay, we're going to assume that this guy is true. This always has an equal sign. Okay. The alternative, often what we'll try to show. If the null hypothesis is rejected, then we accept the alternative. It either has a greater than, less than, or equals or not equal sign. Okay. One-sided alternative, less than or greater than. Only interested in showing the true population is greater right-tailed or less left-tailed than the null. Okay, so we're either looking for this thing or we're looking for this thing. Okay, how far away? Okay, what are we doing, left or right? Two-sided is when we're concerned about how far away from the middle this thing is. And so we have tails on both sides. Okay, we're only interested in showing the true proportion is different from the null. That's not equal. Whereas this would be how much less than, okay, the null, and this is how much greater than the null. Okay, so we're going to set up our normal distributions, okay, based on our claims. Okay, tips. Always use a parameter notation. Okay, mu, p, and sigma. Not statistic notation. X bar, p, p hat, and s. We do not want that. Okay, now when we go to calculate our statistics, we're going to use these. But for our hypotheses, writing the hypotheses, we always want our parameter notation. Okay, number two, think about the alternative. Are we interested in only one direction? Okay, greater or less, or we just want to show a difference? And if it's a difference, then it's not equals. Okay, if it's greater or less, then it's the greater than or less than symbol, right? Okay, we use P naught and mu naught to represent the values of our null hypothesis. Okay, P naught and mu naught. Okay, let's write the null and alternative hypotheses here. Okay, in order to win an election, you need to get more than 50% of the vote. More than 50% of the vote. A sample of voters was polled to see if you are likely to win. Write a null and alternative hypothesis to see if the poll supporters, if the poll supports a win in the actual election. We want to know, is the poll going to support a win? Oh, what's the null, or H naught? Okay, H sub 0. Okay, H naught. Okay, our null. Okay, this is the null. The null is H sub 0. That's always going to be an equal sign. We're going to say that what? Is this a proportion or a mean? Well, it's a proportion, right? So this is P is our parameter for proportion. P is equal to 0.50. We could add the 0 if we want. Okay. Okay, what's the null? I'm sorry, what's the alternative? We did the null. What's the alternative here? Okay, the alternative, okay, H sub A, okay, H sub A, that's the alternative, okay. What's the alternative? Well, a win in our claim, okay, is that we would get above 50%. That's what we're looking for. We're looking for, okay, that win. We're saying, oh, it's either equal to 50 or it's greater than 50, because greater than 50 indicates a win. And that's what we're looking for. We're looking for, is this a win or not? Okay. Now, exactly 50% is not a win. That's a tie, right? That's a tie. So it's a tie or less. We don't need to put the or less because even if we go up to 50%, we still didn't win. We have to be above 50%. That's why it's greater than symbol for it to be a win. Okay. So this is the null and the alternative. Okay. Let's go to example 3 here. John claims his free throw shooting percentage is 85%. That's his claim. To prove it, he shoots 50 shots, makes 37 of them, giving him a 75% shooting percentage. Write the hypothesis used to test the claim. Okay, so what's his claim? His claim is that he's an 85% shooter, right? So that's a proportion. So H sub 0, okay? The claim is that he is at 85%. Okay, what's the alternative? The alternative is that his claim is bogus. Okay, that he is not an 85% shooter. The alternative is that he is less than 85%. Okay. That's the alternative. So his claim is that he is an 85% shooter. Okay, the alternative is that he's not an 85% shooter. Okay, step 3. Okay, step 3 would be, is it independent, random, or large enough? We want to test, you know, is the central limit theorem satisfied? Is the CLT satisfied? Okay, CLT. Okay, can I use a normal distribution? Can I use a normal distribution? Well, we're going to assume independent, okay, that n is less than 5% of the population size, okay, large population. We're going to assume large population. We're going to assume that it's random, that they were randomly sampled. So these two we're just going to assume is true. Okay, and is it large enough? This is, again, what we had to do on our proportions, our confidence intervals, is we had to say, is this large enough? Is the number of successes greater than 10? And is the number of failures greater than 10? Okay, is what I'm looking for greater than equal to 10 in my sample. Okay, is my sample large enough, okay, to approximate a normal curve? Okay, approximate a normal curve. Okay. Okay, here we have a z-score. Okay, recall, what is a z-score? Okay, what does the z-score measure? Okay, if I said that I had a z-score, okay, of say -2, okay, and +2, what do those z-scores represent? Well, it's the number of standard deviations away from the mean. Okay, it's the number of standard deviations away from the mean. Okay. For a proportion, okay, we're going to calculate our z-score. The test statistic is always the statistic, okay, this is our sample proportion, minus the parameter, this is our population proportion, so this is sample proportion, this is population proportion, all over our standard deviation, which in this case, we're going to call our standard error. Okay, that's our standard error there from the confidence intervals. Okay, the test statistic represents the number of, in this case, the number of standard errors. Our result is from our expected parameter, okay, away from our expected parameter. Okay. Okay, So let's go back to our basketball example here. Says John claims his free throw shooting percentage is 85%. Okay, so John claims his free throw shooting is 85%. To prove it, he shoots 50 shots and makes 37. Okay. Okay. If John was really telling the truth, how many standard deviations of below his true shooting percentage did he shoot? Okay. So I'm actually going to go through the whole thing here, but we're really looking for how many standard errors below the true percentage did he shoot? Okay. Okay, or what is believed to be his true percentage. So we're going to go the null hypothesis here, which we found before, p equals 0.85. Okay, the alternative hypothesis, okay, is, okay, the alternative hypothesis, yeah, okay, is p is less than 0.85. Okay, so if we're setting up for a normal distribution, we want to find out how far away from 0.85 is this 0.75. Okay, how far below, how many standard errors away from 0.85 is 0.75? That's what I want to know. And if it's too many standard errors below, if it's way far away from what I'm looking for, then I'm going to call BS on the fact that he's making 85%. He's not an 85% shooter. Okay, he's only a 75% shooter. If it's close enough, then that's fine. Okay, then there's no evidence. But if it's way far away, I'm going to say I'm 95% certain that there's no way he's a 75% shooter. Okay, or I'm 99% sure that I'm never going to be 100% sure, but I'm going to be darn close. Okay, it's an educated guess. Okay. Okay, so what are we going to use here as our test? We're going to use what's called a one prop Z test. Okay, and we'll talk a little bit more about that in a little bit. So one prop Z test, it's one proportion. We're comparing one proportion, and it's a Z curve. Okay, Z curve, and it's a hypothesis test. Okay, one prop Z test. Okay. Okay, number 3 says, is this even possible? Okay, is this even possible to compare it to a normal curve? Well, is the population large? Large population? Sure, we're going to go with that. Is it random? Is it a random sample? Sure, we're going to go with that. Number 3 is N times P. Okay, well, how many shots did he do? N times P. Is that greater than 10? Okay, greater than or equal to 10. Well, what is N? N is 50. What's P? P is 85%. Okay, is that greater than 10? Well, okay, in this case, 50 times 0.85. Let's see what that is. I think it's 37.5 something. 50 times 0.85. Oh, sorry, 42.5 is greater than or equal to 10. Yep, check. Okay. So what about NP equals, okay, 50 times 0.15. Okay. So this is 50 times 0.15. Okay, that's 7.5. 7.5, is that greater than or equal to 10? No, that's not. So we cannot do the hypothesis test on this one. Okay. Could we still calculate how many standard errors he's away? Yeah, we could. Okay, we could find our Z-score. Okay, that's all they're really asking for us to do anyway. If John was really telling the truth, how many standard deviations below? Okay, still it's not a large enough large enough sample for us to run the test, so the test would fail. Okay, but what is the z-score? The z-score is p hat, that's 0.75, minus p naught, which is 0.85, all over the square root of 0.85 times 0.15, okay, all over the number of items, that's 50. Okay, and if I calculate this, this becomes negative 1.98. So I would be about 2 standard deviations below, okay, if I were to calculate that out, that z-score. Okay, about 2 standard errors below. Okay, but again, I can't continue with this. I cannot continue with this because I have an insufficient sample size. Okay. Okay, let's talk about the p-value. Okay, p-value. The p-value of a hypothesis test is the probability of obtaining the observed value of our given statistic. Okay, it's the probability. P-value is the probability. Okay, so let's talk about our example where we had 50 as our mean. Okay, 50 is our mean, and we scored 19 out of 20, or 95% on the exam. Okay, 50 is our mean for a claim of guessing 95%, right? So what's our p-value? Well, our p-value would be the probability of getting 95%. Okay, it's a conditional probability. What is the probability, okay, of obtaining the observed value given that the null hypothesis is true? Okay, given that 0.5 is our null or our mean value, what's the probability of getting a 95%? Okay, or above. Okay, so that's my p-value. Okay, and that I would just use, okay, a normal CDF. Oops. Normal CDF. Okay, to calculate this, right? I would just be like, oh, what's the low? Would be 0.95. What's the high? Infinity. What's the mean? The mean is 0.5. What's the standard error? Okay, the standard error would be the square root of 0.5 times 0.5 all over my sample size. And in this case, I would just have one sample. Okay, so it didn't matter. Okay, because I would just take that one person's test. Okay, not a bunch of people's tests. But again, okay, we would just run it and find the probability of that occurring. Okay. Okay, I'm not going to calculate it out. It's just, okay, as an example. Okay, is this going to be statistically significant or not? We say that the result is considered statistically significant, okay, if the result is unlikely to happen, okay, by pure chance, okay, or a low probability of happening, okay, a low p-value, okay, low probability or low p-value. Okay, how small of a probability is too small? Okay, how small is too small? What's our area of rejection? Okay, we often compare our p-value to 0.05, okay, or 5%. We call that alpha. We say alpha is equal to 0.05. Okay, alpha is this little fish symbol. Okay, it's a Greek letter A. okay, alpha equals, okay, 0.05 is often considered unlikely. We call this value our level of significance, okay? However, we can choose any small probability as our level of significance. The smaller the value we choose, the stronger the evidence. It is important, though, that we select an alpha before performing the hypothesis test. We do not want to sway the conclusion based on our results. Okay, common levels of significance are 1%, 5%, and 10%. Okay, we often, if it doesn't tell you what to use, okay, in a question, this is our default. Okay, sometimes the question does not tell you, okay, it does not tell you what your alpha is or what your level of significance is. And if it doesn't tell you what the level of significance is, then we use 0.05 as a default. Okay, it's just a good overall 2 standard deviations from the mean. If we are more than 2 standard deviations from the mean, then that's highly unlikely to happen. And so we use it as a good default rejection value. Okay, it's an area of rejection. Okay, writing conclusions. Okay, writing conclusions. Okay, for if we're going to reject, say that the p-value is less than alpha. Okay, we get a very small p-value. Okay, since we write it as this, since the p-value of blank is less than alpha, we reject the null hypothesis. There is sufficient evidence to show that blank, okay, and then you have to state, it is, there's sufficient evidence to show that we reject the null hypothesis. Okay, we reject the claim. Okay, we call BS on the claim. Okay, what about failing to reject? Okay, this is if we have a large p-value. Okay, this is a large p-value. The p-value is greater than alpha, then we fail to reject. Okay, we fail to reject. Since the p-value of blank is greater than alpha, we fail to reject the null hypothesis. There is not enough evidence to show that the claim is false. Okay, there's not enough evidence to show that the claim is false, whatever that claim is. He could possibly make 85% of his free throws if we have a large p-value. If we have a small p-value, we're gonna call BS on his claim and say no. Okay, your free throw shooting average, okay, or proportion is not what you're saying it is. Okay, and we have evidence to support that. Okay, let's calculate a p-value. Let's practice calculating a p-value. Okay. Example 5. The percentage of all college graduates in the nation who have a LinkedIn account is 32%. Okay. 275 graduates from one particular college had 38% of graduates with a LinkedIn account. How many standard deviations above the overall percentage is this particular college? Okay, so do they follow the national average? So that's a z-score. I'm calculating a z-score. Okay, I want p hat minus p all over the square root of p q over n. Okay, we're going to calculate a z-score here. Okay, so what is p hat? This is the percentage of the sample. Well, the percentage of the sample is 38%. Okay, 38%. What's the percentage of the claim? What's the claim? The claim is that they have The nation is at 32%. Well, what's the percentage of the population that we're claiming against? 32%. Okay. Let's calculate the standard, how many standard errors away from the mean this is. This is going to be 0.32 times 0.68, okay, P times Q, all over 275, which is N. And this, if you calculate this on a calculator, okay, this comes out to be 2.13. Let's do that real quick, just to make sure that we know how to input this into the calculator properly. Okay, now this is a fraction, fraction over fraction, that's implied parentheses. 0.38 on top minus 0.32. Okay, close parenthesis, that's what goes on top. On bottom, I'm going to get the square root function. Now the square root function is going to give me parentheses, which is nice. So it's the square root of everything here, okay, under the square root symbol is 0.32 times 0.68 divided by 275, okay, looks good. And I get about 2.13 as my z-score. This is my z-score, okay, that's my z-score. Okay, what is the probability of this z-score occurring? What's the probability of this z-score occurring? Well, what's the probability of the school having a proportion that is much higher than the national rate? Okay, what's the probability that they are 2.13 standard deviations above the mean? Okay, here's the mean, would be 0. Okay, we want, what's the probability that z is greater than 2.13? Okay, this is going to be normal CDF of just a normal curve, standard normal curve. So second vars, normal CDF. Okay, we want the lower to be 2.13. Okay, the upper to be positive infinity. That's what we're testing here. Okay, positive infinity. Okay, so that's 1E99. Okay, 0, 1 is fine because it's a standard normal curve. And we paste that and we get 0.0166, we'll say. Okay, and that's the probability. So less than 1% of this actually occurring. Or sorry, less than 2% of this actually occurring. If alpha was 0.05, okay, we would say that 0.0166 is less than 0.05. And if we had a hypothesis here, let's say that HO was that the proportion of graduates was equal to 32.32, and the alternative was that the proportion was greater than 0.32, right? And so what would we do in this case? In this case, we would say that if we use an alpha of 0.05, we would actually reject the claim. We would say that no, there's no way. Okay, they're at 0.38. We would reject the claim that they are at the national average. Okay, we would reject the null. Okay, and we would accept our alternative. Okay, because our p value is less than alpha. Oops, not infinity. less than alpha. Okay, since our p-value is less than alpha, okay, we reject the null. We reject the null. If our p-value is greater than alpha, then we fail to reject the null. Okay, we don't. We fail to reject. We fail to commit. Okay. Okay, let's go into a full-blown hypothesis test. Okay, 5-step process. We're going to do the whole thing. Okay, we're going to do 2 whole hypothesis tests now. Okay, these things are kind of long. They take a lot of calculation, and they take a lot of interpretation. Okay, you will have a few of these to do on the next exam. Okay, so keep that in mind. You need to know how to do a hypothesis test. Okay, a large city's DMV claimed that 80% of candidates passed driving tests. But a survey of 90 randomly selected teens who had taken the test found only 61 passed. Okay, only 61 who passed. Perform a test to see if the pass rate for teens in this location is significantly lower than the DMV claim. Okay. Okay, so what do we want to do first? What's our first step here? Okay, our first step is to define the parameter, the null and the alternative hypotheses. Okay, so what's the parameter? What's the parameter? What's the population value? Okay, what's the parameter? What's P in this case? The population proportion. A large city's DMV claimed that 80% of candidates, okay, pass driving tests. Okay, so that's my claim. My claim is that 80%, right? So P equals 0.80. My population proportion is equal to 80%. That's my claim. Okay, that's the DMV's claim. The DMV is claiming that 80% pass. Right? So that's my null hypothesis. My null hypothesis, okay, is that P is equal to 0.80. That's my null. Okay, that's what I'm testing against. What's my alternative? And again, P, the equal sign always goes with the null. Okay, the equal sign always goes with the null. Okay. So now what are we testing? What's our alternative? Well, if it's equal, it could either be greater than or it could be lower than, right? We could have an alternative that's either greater, or we could have an alternative that's not equals, or we could have an alternative that's lower. So in this case, okay, what are we looking for? We're looking for perform a test to see if the pass rate for teams in this location is significantly lower. So that implies that we're going to use a less than symbol. Okay, P is less than 80%. We want to know, is it less than? Is it equals or greater than? Okay, equals or greater than. But we don't need to put the greater than. We're just testing against the equal sign. Okay, that's step 1. Step 1 is done. Okay, number 2, name the test. What type of test are we using? Well, we're using proportions, and we're using a Z, okay, normal distribution to test against with our proportions, and we're only using one proportion. So this is called a one proportion z-test. Okay, one proportion z-test. And usually that's hyphenated. Okay, one proportion z-test. Okay, or we call it a one prop z-test. Okay, if you want to abbreviate it, that's fine. One prop z-test. Okay, number 3. Check the requirements. Can we even perform the test? The last time we couldn't perform the test because the requirements weren't met. Okay. Okay, number 3. Is it a large population? Is it a large city? Sure, cities are large. Check. Okay. Is it random? Okay, were they randomly selected? Well, were they randomly selected? Well, it says right in the problem that they were randomly selected. Check. Is it a large enough sample? Okay, how many were chosen? What's n? N is 90 in this case, right? So how many were chosen? 90 students, 90 students. So what's n times p? What's 90 times 0.80? Well, that's 72. And that is greater than or equal to 10, so that checks. Okay. What's NQ? NQ is 90 times the complement of 80%. Well, what's the complement of 80%? Well, that's 20%. So if 80% passed, then 20% failed. And this equals 18, which is again greater than or equal to 10. So good, well, requirements are met. Nice. Again, otherwise we could not go on to the next step. Number 4, let's check let's calculate our statistics. Okay. Okay, what's p hat in this case? What's p hat? P hat, oops. Okay, p hat is our sample proportion. How many students passed? Well, 61. Out of how many total students? 90. So that's our p hat. 61 out of 90 is our p hat. That's our sample proportion. It's our sample proportion. Okay. Okay, so how are we going to calculate our z-score? Well, to get our z-score, it's going to be, okay, p hat minus p naught, all over the square root of p q over n, okay, because it's sample proportion. So what's p hat? P hat is 61 over 90. I'm not going to make it a decimal just yet, because I don't want rounding error. Minus our population proportion, which is 80%, all over the square root of 80% times 20%, all over our sample size, which is n. Okay. And let's look at the calculator on this one. Okay. Okay, so I'm going to do parentheses. 61 divided by 90 minus 0.80. Okay, that's the top. Over the bottom, square root okay, of 0.8 times 0.2 divided by 90. Okay, and that comes out to be about negative 2.899. Okay, negative 2.899. Okay, negative 2.899. Okay, so what's my p-value in this case? What's my p-value? Okay, p-value is the probability that I would be what? That I would be less than, right? Because again, going back to our alternative, it's less than, it's lower, okay? Less than, the probability that z is less than negative 2.899. What's the probability to be less than 2.899? Okay. So this, we're going to go to normal CDF. Okay, and we want to know what's the probability of being less than negative 2.899. So we're going to go from negative infinity, okay, negative infinity all the way up to negative 2.899. 0, 1 is fine because it's a z-score, and that's 0.000, sorry, 0019, 0.0019. Okay, now they didn't give me what alpha was, so I'm going to assume alpha is 0.05. We're going to assume alpha, what we're testing against is 0.05. We're going to assume that it's 0.05. So we're going to test this. How does p, the p-value, compare to alpha? Well, 0.0019 is significantly less than 0.05. Okay, it's much, much less. And if our p-value is less than alpha, then we reject the null. We reject the null and accept the alternative. Okay, reject the null and accept all the alternative. Okay, so what does this mean? Let's do number 5 here. Okay, number 5 is to write a conclusion, interpret in terms of the problem. What is our conclusion? Well, our conclusion was that we rejected the null, okay, and we accepted the alternative. Well, what's the alternative? The alternative is that it's not 80%. It's significantly lower than 80%. Okay, that's the pass rate. So we say there is evidence to suggest that the city's pass rate is significantly lower than 80%. That's our conclusion. That's our answer. Okay, there is evidence to suggest that the city's pass rate is significantly lower than 80%. Okay, now all of number 4 here could have been done on the calculator, okay, or on StatCrunch. So I want to go over how would we do number 4 on the calculator and StatCrunch, okay, because the calculator and StatCrunch will produce all these numbers for us. And again, this p-value is really what I want. That's really what I'm going for. Okay, that's the end game here. The end game is what's the p-value? If it's bigger, I do not reject. If it's smaller, I do reject. Okay? If it's bigger, I don't reject. If it's smaller, I do reject. Okay? If it's smaller, I say BS to your claim. Your claim is bogus. Okay? If it's bigger, I'm like, I'm not sure, so I'm gonna allow it to be accepted. I failed to reject. Okay? I failed to commit. Okay, so let's see, how would we run number 4 on the calculator and have it do it all in one shot? Well, if we go to stat, hit the stat key. Okay, so for the TI, okay, this is going to be stat and then tests. Okay, we're going to run all the way over to test. Test is hypothesis test. Well, that's nice. Okay, tests, and then we're going to do 5 for test. That's a 1 prop Z test. Look at that. It has 1 prop Z test right there for me. Okay, for number 5, 1 prop Z test. Oh, okay, that's kind of cool. Okay, so let's hit number 5, and it says, okay, what's your null hypothesis? What's your null proportion? And my null proportion was 80%. That's what I was comparing against, was the claim. That's my null. My null is the claim. What's X? X is the number of successes that I got, the number of successes. That's the number on top for the sample proportion. Well, that's 61. I got 61 passes out of 90 total trials. 61 passes out of 90 trials. That's about 67%. Okay, and it says, what do you want to compare against? Do you want to compare for your null? Do you want this to be not equal to, less than, or greater than? Do you want it to be not equal to, less than, or greater than? Well, I want it to be less than. I want to compare less than my null hypothesis. I'm going to hit arrow over, I'm going to hit enter, and that's going to give me less than. And then I'm going to arrow down, I'm going to hit calculate. And look at that. It tells me what my Z value was, my Z score, boom, negative 2.89. It also tells me what my P value was. That's that little P there that's next, okay, is 0.008. It tells me what my P hat was. My P hat was 0.67, or sorry, 0.68. And my N was 90, which is what I told it. So again, this is P. The P value is that P score that it's giving me. And it says, hey, given that information, the calculator is gonna spit out, okay, it's gonna go through all of these computations, and it's going to give me the P value that I'm looking for. And then I compare it against my alpha, and I come up with a conclusion. You come up with a conclusion. Okay. Okay, let's try one more. Let me go get a bottle of water. My throat is dry. I'll be right back. Okay, much better. Thank you. Okay, example 7. It says in 2005, the Department of Education claimed that 60% of graduates are prepared to manage their own finances. In 2015, out of a sample of 500, 327 responded that they felt prepared to manage their own finances. Is there evidence that the proportion of graduates who are prepared has changed from 2005 to 2015? Okay. Okay, so let's go through our 5 steps here. Number 1, let's write our null and our alternative. What's our null? Okay, what's our H sub O? Okay, H sub 0. Okay, what's our null? Okay, we're comparing this against the claim, So our parameter is P because it's a proportion. Okay, P. And what is it claiming? It's claiming that in 2005, the proportion was 60%, right? 60%, 0.60. Okay, what's the alternative? What's the alternative? What's H sub A? The alternative is that it has changed. It's changed. Well, how do we designate change? It doesn't say that it's gone up. It doesn't say that it's gone down. It just says that it is changed. Well, that it's not equal to 0.60. This is two-tailed. It's called a two-tailed test. We just want to know, has it deviated away from 0.6 and how much? Okay, why is it called two-tailed? Because we're splitting up the testing region into 2 tails. Okay, so we just want to know how far away from 0.6 in either direction has it gone. Before we were just interested in one direction. Okay, not to be confused with the famous boy band from the early 2000s. Okay, 2 tails. Okay, 2 tails. Okay, before we were just going one direction, but now we have 2 directions to worry about. Okay, it's 2 tails. Okay, that's the not equal sign. Not equal sign. That's what keys you into the not equal sign is the change here. Okay, it's the change. Okay, number 2. What type of proportion test are we using here? We're doing a 1 prop Z test. Okay, 1 prop Z test. Okay. Okay. Number 3, can we even run the test? Okay, is it a large population? Large population, sure. Is it a random sample? Sure. Okay, large population. The Department of Education, yeah, I would say that's a large population. Okay, is it randomly? Are they randomly assigned? Sure. We're going to assume random. Okay, is n times p greater than or equal to 10? Well, what is n times p? This is 500 times, well, n times p is equal to x. And x is the number of successes, right? It's the number of successes. So that's 327. So yeah, I would say that 327 is greater than or equal to 10. Okay, what about n times q? Is that greater than or equal to 10? Well, what is n times q? Well, it's the ones that didn't pass. Okay, or sorry, the ones that aren't prepared. That's 500 minus 327, which is, whoops, I did this wrong. It's not 327, I'm sorry. This should be, oh, I screwed up, my bad. Let's go back to this one. This is n times p. N is 500. N is 500. That's how many were in my sample. Okay, n is 500, and p is my population proportion. Okay, not x. My bad. Okay, p is my population proportion. That's 0.6, which is equal to 300 students, which is greater than or equal to 10. Okay, what's n times q? Is that greater than or equal to 10? Okay, that's 500 times 0.4, which is 200, and that is greater than or equal to 10, so that checks. Okay, they both check. All criteria is good. We are ready for go for number 4. Number 4, I'm going to do on the calculator. Okay, I'm going to do on the calculator. I want to find my p-value. My p-value is equal to what? I'm going to go to the calculator. I'm going to go one prop z test. Okay, so I'm going to go to stats, test, one prop z test. I'm going to plug in my null hypothesis value of 0.6. Okay, X is the number of successes in my sample. That
Do
was,
you think you can do StatCrunch with this one?
yeah, absolutely. I was going to do it anyway. But yeah, thank you. I will. Okay, 327, n is equal to 500. Okay, and this is going to be a not equals. Okay, because it's changed. And now I'm going to calculate this one. Okay, I hit calculate. My p-value ends up being, okay, 0.0137. Okay, so let's do this on StatCrunch real quick. Okay, let's calculate the same p-value. Okay, it's very easy on StatCrunch. You just go to tests. Okay, you go to prop stats, prop proportion, I don't remember, but it's the same thing that we used. It's the same thing we used for confidence interval. Okay. We're just going to, instead of doing a confidence interval, we're going to do a hypothesis test. Hypothesis test and confidence intervals are very similar to each other. Okay. A two-tailed test is basically a confidence interval. Okay, so we're going to go to stat, and we're going to go to proportion statistics. And we're going to go to one sample. Let's try that again. Proportion statistics. What the heck? It's not liking my pen. Okay, stat, proportion statistics, one sample with summary. We don't want the data. We want the summary stats. Okay. So it says, what are your number of successes? Well, my number of successes were 327. Oops, sorry. Okay, what are my number of observations? Well, there were 500, right? 500. I want a hypothesis test. Okay, for P, yeah, that's what I want. I want a hypothesis test for P. P is equal to what? What's my null? My null is 0.6. What's my alternative? My alternative, I could choose from not equal to, less than, or greater than. In this case, I want the default, which is not equal to. Okay, and then it says down here, I don't know if you can see it. Okay, it says compute, okay, at the very bottom. compute. And it says, oh, what's your p-value? Your p-value is right here. Your z-score was 2.46 and your p-value was 0.0137. Okay, that's how we would get this one. Let's say that we wanted to get the last one. How do we do the last one? Okay, again, very simple. Stats, proportion stats, one sample with summary. Number of successes was 61. Keep doing that. Number of observation was 90. We wanted to compare it against an 80%. 80%. In this case, we wanted it to be less than. Okay, that was for the last one. And it says, look, what's our p-value? Our p-value is 0.0019. Okay, which is exactly what we found it to be in the previous example. So StatCrunch is super easy. Okay, StatCrunch super easy. Okay. Okay, so now once we have our p-value, okay, now that we have our p-value, well, what does this tell us? We're going to use alpha equaling 0.05. So our p-value is less than 0.05. So what does that tell me to do? Okay, yeah, it tells me to reject the null. What am I going to do? I'm going to reject the null. Okay, I'm going to reject my hoe. Okay, because that's what you do. Okay, so reject the null here, and we're going to do 0.037 is less than 0.05. We're going to accept the alternative that what? We're going to accept the alternative that it has changed. Okay, so since our p-value is less than the significance level of 0.05, we reject the claim that what? That 80% of candidates pass their exam okay.
You're reading a wrong question.
Oh, yes, thank you.
You're welcome.
Thank you. Okay, that what? That they manage their own finances. We reject the null, okay, and accept that the proportion of students or graduates, however you want to say it, proportion of graduates. Okay, reject the null and accept that the proportion of graduates who are prepared to manage their own finances, who are prepared to manage their own finances has done what? Has done what? What's the alternative? The alternative is that it's not equal to, which implies that it's changed, right? That it's changed. Who are prepared to manage their own finances has changed We don't know if it went up or if it went down. All we care about is that it's changed, is that it has changed from 2005 to 2015. Okay, boom, period. That's our conclusion. Okay, written in a sentence. Okay, don't just tell me that you reject the null. Reject the null is not a conclusion. Okay, you will get marked off for that on the exam. Okay, it has to be placed in the context of the scenario. What is the rejecting of the null tell me about the original problem, about the original claim? It means that the original claim here was bogus. Okay, it was a bogus claim. And we say, no, we are 95% certain that you're wrong, that it is less than, okay, sorry, that it is not equal to, okay, 60%. It has changed. Okay. Okay, what I'd like you to do now is to, start working on your homework. Okay, either finish up 8.3 or work on 9.1. Okay, and I'll be here to field questions, and I think Gabrielle should be here as well, right? Okay, and she's here to field questions as well. Yep, there she is. Okay, now I did post an announcement. Okay, same things that I've been posting, which was, I'm gonna do a new share here. Okay. Log in. Okay. Canvas. Okay. Can everybody see my Canvas page? Is it good?
Yes.
Okay, thank you. Okay, so if we go to Canvas, okay, so I updated this. Oh no, I sent out an announcement. Okay, and I also updated something. Okay, so again, there are some tutoring hours. I don't know what this is. Let's try this again. Free tutoring, okay, is available here. Okay, Monday, Wednesday, and Thursday. Okay, so math tutoring, math online tutoring. Okay, so again, this may or may not fit into your schedule. And I understand that, but we are here for 4 hours during the week to help you out. One-on-one math tutoring usually. Okay. Professor Sweeney and me, Professor Holtman, are doing math tutoring Monday, Wednesday, and Thursday. So, be sure to check that out if you're available to come. Okay. Also, they have statistics tutoring. Okay. And that should be on the home page here. So free statistics tutoring, okay, through the Math Center. Okay, also through these workshops. So it says SAC workshop here, okay, Monday through Thursday in the morning, 11 to 2, and at night, 5 to 8. So maybe on the days that you don't come to class Monday, Wednesday, you could go to the tutoring session from 5 to 8. Okay, you can join from any electronic device. And here are the links to those. These are updated links, okay, to those sessions. These are for statistics, okay, specifically for statistics. Okay, so there's also the Math Center that's open till 9 o'clock every day. Okay, 9 p.m. as well, where you can get one-on-one tutoring there as well through Zoom. Okay, one-on-one tutoring through Zoom there as well, and that's about it. Okay, so a lot of opportunities to get tutoring. Okay, and there's also in-class tutoring right now. Okay. Okay, so let me know if you have questions. Let Gabriella know as well if you need her on a question. We'll be here. Okay, so
I have a question regarding grades.
yes.
So the grade in Canvas is what we have right now. That's pretty accurate.
Yeah, should be.
Okay, just wanted to make sure.
Yeah, should be up to date. Whatever yeah, because I put in the grades from the last exam. So, and then whatever the homework grade that goes in tonight will be your
Okay.
latest grade. Okay. Yeah, they're up to date. Okay. So let me know if you need any help on anything. Otherwise, you can work quietly for the next hour. Okay.